Welcome to this module, and here we will see the application of operational amplifiers. So, until what we were learning in the previous lecture were the characteristics of an operational amplifier. So, when you talk about the characteristics, we have seen several characteristics of operational amplifier, including its input impedance, its output impedance, high gain, right, and then we have seen how offset voltages comes into play, what is input bias current, and then we have see how CMRR comes into play, and what exactly CMRR is, and how we can change the how the CMRR should be if it is very high, how it is useful to get the actual output voltage of our desired value, and we can reduce the common mode voltage if the CMRR is extremely high. We have seen that example as well. We have also seen how can we use the operational amplifier and what kind of circuits we can use to nullify the effect of the offset, or how can we offset the output voltage such that our output will be nullified or output should be 0. That means that when we apply ground to both the terminals, our output should be 0. So, what we can do? So, we have seen that circuit that we can connect between terminal 1 and terminal 5 a potentiometer, and by changing the value of the potentiometer we will be able to see the output voltage equal to 0. Then we have also seen the input effect of input bias current, input offset current, and how we can determine given the values of input offset and input bias current or input currents when you are given, then how can you determine the those values. So, once we have understood, and we have also seen about the virtual ground, right, very important concept of virtual ground we have also seen. Now, using all these things, that is our basic, how we can implement the different operational amplifier circuits. That is the idea, and that is today's lecture. So, this lecture is our class 10 and or lecture 10, and it is divided into several modules. So, to help you out to understand how the op amp circuits can be designed. So, when you talk about operational amplifier circuits, what we see that the operational amplifier circuits configuration includes several different applications, starting from the unity gain amplifier or unity gain buffer. Then we have seen inverting amplifier, then we have seen non-inverting amplifier, sorry, we have not seen this, we will see inverting amplifier, non-inverting amplifier, then we will see summing amplifier, we will see integrator, we will see differentiator, and not only that, we will also see filters, right, we will also see filters. So, that will be, these filters will be our next lecture. For this particular lecture, we will see the following amplifiers. We will take few problems and we will try to solve it. So, we understand how we can design operational amplifier based circuits, alright. So, like we have seen, there are several kind of circuits. We should start understanding the first one, which is the voltage follower circuit. So, if you can see on the screen, what we see is a unity gain buffer based on non-inverting configuration. What does that mean? That if I apply a voltage at the non-inverting input, right, and I have a feedback to the inverting, the output is feedback to the inverting here, right. This becomes our unity gain buffer. This is unity gain buffer based on non-inverting configuration, because we are applying voltage to the non-inverting amplifier, right. We have seen this application earlier also. Equivalent voltage amplifier model. So, if I make an equivalent voltage amplifier model, how can I use it? You can see that the input resistance of the voltage follower, input resistance is infinite, right, output resistance is 0, voltage gain of the unity gain amplifier, that is why it is called unity gain. Unity gain means what? Gain is 1, right. So, to have gain equal to 1, right, we have AVO, voltage gain, equal to 1, alright. The closed loop gain is unity regardless of source or load. So, this is our unity gain amplifier. It is also used as a buffer voltage amplifier to connect a source with high input impedance to a low input impedance load, right. Why? Because the unity gain amplifier has a high input impedance, and it has a low output impedance. That means that it can be connected to a source, suppose the source is this one, right, which has extremely high input impedance. Then we can connect the unity gain amplifier, and the load will have extremely low output impedance, okay, low impedance load. Then we can connect the unity gain amplifier. Unity gain amplifier is also used as a last stage of most of the amplifying circuit, because it is a voltage follower, and it can be connected to any load which will draw a lot of current, but the voltage at the input will be same at the output. The voltage will follow. The voltage, whatever voltage is at input, it will follow at the output. So, output voltage follows the input voltage, right. That is why it is also called voltage follower. The gain is 1, that is why it is also called unity gain amplifier. Okay. So, these are the characteristics of operational amplifier, particularly as a voltage follower. This is how we can use operational amplifier as a voltage follower. Now, let us see further the inverting amplifier. Okay, inverting amplifier. So, how we can design a circuit of an inverting amplifier using a op amp, So, the inverting closed loop configuration, external components R1 and R2 form a closed loop. Here you can see R1 and R2, right. This forms a closed loop because you are feeding back here, see here, and input signal is applied from the inverting terminal. So, we are applying the input to the inverting terminal. Okay. So, 3 things we have to understand: external components R1 and R2, that forms closed loop. Second, output is fed back to the inverting input, and third is that input signal is applied to the inverting terminal. Okay. Now, the required condition to apply virtual short op amp circuit, right, is negative feedback and infinite open loop gain. These are the requirements, isn't it? So, what if there is a closed loop gain? So, closed loop gain G equals to VO by VI, right, VO by VI, which is nothing but minus R2 by R1. See, if I see here, you see at this point it will be virtual ground. We have seen the concept of virtual ground, right, because this terminal is grounded, our inverting terminal is grounded. That is why the point at non inverting terminal will also be considered as ground, a virtual ground. So, if I have a resistor R1, I apply voltage V1, then the current flowing through my resistor R1 would be nothing but I equals to V by R1. Similarly, if I want to measure the current flowing through R2, it will be nothing but I2 equals to I1 equals to V1 by R1. So, what will be my output voltage? It is 0 here, right. Here voltage is 0 because nothing will flow here, it is a infinite input impedance and or very high input impedance, and the difference voltage is also 0 volt. So, if I want to measure VO, VO is nothing but 0 minus V1 by R1 into R2, right, V1 by R1 into R2. So, what will be VO? VO will be nothing but minus R2 by R1, correct. VO will be nothing but minus R2 by R1. Now, if you see infinite differential gain is V2 minus V1 is nothing but VO by A is nothing but 0, right. Infinite differential gain will be 0 because of infinite differential gain, right, the value here is 0. Infinite input impedance, right, we know that it has infinite input impedance, that means my I1 equals to I2 equals to 0. Then I have 0 output impedance, that means my output voltage will be nothing but VO equals to V1 minus I1 R2, that is correct. VO equals to what? V1 minus I1 into R2, right, because you see here is same, this is R2. So, I have VO equals to nothing but VO equals to V1 minus I1 R2, right. So, if I substitute the value, what will I have? output equals to minus V 1 R 2 by R 1, correct. Now, if I take voltage gain is negative, voltage gain is negative, that is correct, because my inverting amplifier, my voltage gain is minus R 2 by R 1, right. My gain is minus R 2 by R 1, voltage gain, then we can multiply by input. So, voltage gain is what? Negative, voltage gain is negative, right. Input and output signals are out of phase. This is another concept, and we have seen this concept, or let us see when you talk about out of phase is nothing but when you apply the input to the inverting terminal, which is right over here, it is applied to the inverting terminal. Input is signal like this, output will be multiplied or amplified version of the input, output would be amplified version of the input, but and that amplification depends on the value of R 2 by R 1, right, value of R 2 by R 1. But the is it in phase or out of phase? This is in phase signal, but in case of inverting amplifier, you will see that the output would be amplified but out of phase, it will be magnified but generally 180 degree out of phase. If this is 0 degree, is 180 degree out of phase. Okay. So, that is what is written here, that input signals and output signals are out of phase. Okay. Next, closed loop gain depends entirely on external passive components, right. Closed loop gain depends on external passive components. Why? Because we have R 2 and R 1, we have R 2 and R 1. So, this is external passive component, R 1 is resistor, R 2 is resistor, these are externally connected to the op amp, that is why they are external passive components. And our gain, this is a closed loop. If you see this amplifier, it is in closed loop configuration. Our closed loop gain depends on the value of R 2 and R 1, and that is why we can say that the closed loop gain depends entirely on external passive components, Closed loop amplifier trades gain for accuracy, right. That means that here we do not have extremely high gain, but we can change the gain and we can have finite but accurate closed loop gain. So, accuracy is better here, but we have finite closed loop gain. Okay. But in case of no feedback, you will have infinite gain. In case of no feedback, you have infinite gain. This is the inverting amplifier. Now, if I draw equivalent circuit model of inverting configuration, what will I have? I have R 1, my gain is minus R 2 by R 1 into V I, I have output voltage V O, input voltage V I, right. So, input impedance is nothing but R I equals to V I by I I or V I by I 1, right, equals to V I divided by V 1 by R 1, that is correct, which is nothing but V cancel or this value will be cancelled. So, it is nothing but 1 divided by 1 by R 1, which is equal to R 1, right. That means my input impedance will depend on the value of resistor R 1. For high input closed loop impedance, R 1 should be large, but is limited to provide sufficient G. What does that mean? That if I have A V equals to, what is my gain here? R 2 by R 1, is not it, right. And if I say output voltage V O is nothing but R 2 by R 1 into input voltage V I, correct. Now, what we are saying here, that for high input closed loop impedance, what we should have? We should have R 1 extremely high, R 1 value should be extremely high. So, if I put R 1 extremely high, what will happen? My output will be similar to my input. Let us say if R 1 is infinite, my out or close to infinite, this R 2 value R 2 by R 1 will be extremely small into V I. So, I cannot do that R 1 can be extremely high, this is not possible, right. Otherwise, this will not work properly. So, what is written? But is limited to provide sufficient gain. That we have to use very high value of R1, but we have to also understand what is the gain of our amplifier. For example, if I want to have gain of amplifier to be 100, right, then I can have R2 which is 100, but R1 I cannot have 100, I can only have 1, right. So, if I have gain of, so I can have R2 equal to 100 k, R1 equal to 1 k, you see. So, it is limited by this gain, it is limited by the gain. Even we want higher, if I put like 10 k here, my gain will not be 100, my gain will become 10, right. Why gain will become 10? Because gain is nothing but minus R2 by R1, right. So, it is limited to provide sufficient gain, alright. This is an example which we have seen. Now, in general the inverting configuration suffers from low input impedance. You see here, why? Because you see here only R2 by R1, if I want to have gain of 100, my R1 would be 1 k if I select R2 equal to 100. 1 k is extremely small, but in reality we should have R1 or input impedance extremely high. So, in case of inverting amplifier, the low input impedance is a problem, or in another terms, inverting amplifier configuration suffers from a low input impedance, alright. Output impedance is 0, voltage gain is nothing but minus R2 by R1. Easy, super easy, right. So, let us solve an example, okay. Let us solve an example. So, find the closed loop gain of following inverting amplifier circuit. You are given a circuit and you are asked to find the closed loop gain, okay. Now, we are already given R in 10, RF 100, right. Then what is our AV? AV is nothing but V out by V in, or we can write minus RF by R in, 100 by 10, both is kilo ohm. So, I do not write it, that is fine, right. So, what I have? Minus 10, but gain cannot be minus, right. So, we always write is equal to 10, gain is equal to 10. So, if I want to understand the closed loop gain, my closed loop gain of the inverting amplifier circuit is 10 or 20 dB or 20 log 10, right. So, this is how I can understand my inverting amplifier. Let us see one more example. Okay. So, the inverting amplifier, the gain of the original circuit is to be increased by 40 dB. Okay. Find the values of resistors. See, we are not given the values of resistor. Okay. Now, what is given? That we have to increase the gain to 40 dB or 40 or 32 dB. So, what will be the value of resistors? What will be value of these resistors? That is the question. Okay. So, given AV equals to 40, right, it is already given, gain is 40. Now, since it is an inverting op amp, is it inverting op amp? Yes, because we are providing input to the inverting terminal. So, what will be my AV? AV will nothing but be AV would be RF by Rn, AV would nothing be but RF by Rn. So, 40 equals to RF by Rn, right, 40 equals to RF by Rn. So, if I assume that my Rin let us say is 10 kilo ohm, then my RF would be what? See, I have this formula, I have AV equals to 40 equals to RF by Rin, alright, implies RF equals to 40 into Rin. If I assume Rin to be 10 kilo ohm, my RF would be 400 kilo ohms. Very easy, super easy, right. If I consider Rin as 1 kilo ohm, then my RF would be 40 kilo ohms. RF would be 40 kilo ohm. If I assume my R in equal to 10 kilo ohm, RF would be 100 kilo ohm, right. If I assume this is 10 kilo ohm, then RF equals to 100 kilo ohm. So, this is how you can solve the question for the inverting amplifier, alright. Let us see one more example, alright. I am giving you more examples so that you can understand when you are given a circuit, how can you solve the problem, okay. So, find Vn, V1, Vo for the circuit shown here, right. For this particular circuit we have to find lot of things. So, let us see. So, if I use the circuit first at node n, right, at node n I have to here I have to find. So, I will use Kirchhoff voltage Kirchhoff current law at node n, and what will I have? I will have I3, I will have I3 and I have I4 here. So, that will be I3 plus I4 equal to 0, correct, according to Kirchhoff current law. This will be I3 plus I4 equals to 0. Now, what is I3? I3 is nothing but V by R. What is V? V is my Vn. V is my Vn. What is R? R is my 10 kilo ohm, right, Vn 10 kilo ohm. So, I substitute this value, correct, plus I4. What is I4? I4 is here. I4 is nothing but you see here. So, it is like Vn minus Vo divided by R4, correct, Vn. So, from here I3 is what? I3 will be my Vn by 10 kilo ohm, right, which is my R3. I3 will be Vn by R3, which is Vn by 10 kilo ohm, right, and I4 equals to Vn minus Vo by R4 equals to Vn minus Vo divided by 20 kilo ohms, right, 20 kilo ohms. This is what I have written here. So, from here when you solve it, you will find that Vn equals to Vo by 3, okay, Vn equals to Vo by 3. Now, Vo minus V1 equals to 6, Vo minus V1 equals to 6 and Vn equals to V1 as per virtual ground, correct. Vo minus V1 equals to 6 because here see what is the output, what is the bias voltage? 6 volt, that is applied across the 3 and Vo, right. So, if I say Vo minus V1, Vo this voltage minus this voltage is nothing but 6 volts, right, and Vn this voltage Vn, right, should be equal to V1, sorry, Vn is here, Vn should be equal to this voltage V1. Why? Because by the concept of virtual ground, by the virtual ground. So, what we have? Vo minus V1 equals to 6 and Vn equals to V1. So, therefore, Vo minus Vn equals to 6. So, Vo will be Vn plus 6. So, Vo will be Vn plus 6. Vn is what? Vn is Vo by 3, right. So, I will put Vo by 3 plus 6. So, Vo would be nothing but 9 volts. Now, I know that Vn equals to V1 equals to 3 volts. How? Because I know Vn equals to Vo by 3 equals to 9 by 3 equals to 3 volts, correct. Vo equals to Vo by 3, Vn equals to Vo by 3, right, this is 3 equals to what is Vo? Vo is 9 volts. So, 9 volts by 3 which is nothing but my 3 volts, right. So, this is how I can find what is the Vn, V1 and Vo for a given circuit. This is how I can find what is Vn, V1 and Vo for the given circuit when you are given a circuit of an inverting amplifier. Okay, guys. Now, let us see an example. Let us see an example of a summing amplifier. So, what is summing amplifier? Let us see the circuit. Okay. So, when you see the circuit, what you find is that when you use inverting amplifier, if you come back on the screen, you will see that we are using an inverting amplifier. We have a feedback resistor, but instead of one input resistor, you have 3. You can have n also. You can have n input resistors. Okay. So, n inputs and the output will be summation of all the inputs. Okay. So, how can we do that? You can, it is written over here. If given, you are given this circuit, then using Kirchhoff current law, using Kirchhoff current law, what we can find? We can find I1, this values, okay, I1, I2, I3, 3 values are given. So, I1 plus I2 plus I3 minus I4 here and here, right. You see this configuration, minus 0 equals to 0, right. So, output voltage would be what? VO equals to minus RF, right. Why? Because it inverting amplifier, this is the inverting amplifier. So, inverting amplifier, our formula is RF by input resistance R in, right. Here first is V1 by R1. Why? Because RF into V1 here, V1 by R1 plus V2 by R2 plus V3 by R3, right. That means output voltage is the summation of the input voltages, and you can change the gain with the help of RF and input resistors. That means it is not only providing a summation, it is also providing the amplification. And that is why what we say is this is an summing amplifier, right. Now, here you can see very easily that the concept of virtual ground will come here, here and here. This is nothing but because the inverting terminal, non-inverting terminal is grounded, the voltage at the inverting terminal is also considered as 0, which is your virtual ground, Now, if you are given an example which is right over here in front of you, this example, design a summing amplifier as shown in figure to produce a specific voltage such that VO equals to this. Assume that V1 is this, V2 is this, and feedback resistor RF is value, RF is of 10 kilo ohm value, right. Now, if you see closely, you are given V in 1, you are given this voltage which is your V in 1, right. Here you are given V in 2, but you are not given anything about Vi3 here. Are you given anything about Vi3? So, we do not have to assume there is Vi3 or Vi3 equals to 0, Now, we can just, we know this formula, right, we know this formula which is similar to here, this formula for summing amplifier. We will substitute the value. So, minus RF remains as it is here. What is Vi1? Vi1 is minus 1 volt divided by R1 plus what is Vi2? Vi2 is nothing but 0.5 cos omega t by R2, right. Now, what is VO? VO is given as 1.25 minus 2.5 cos omega t equals to RF into this value. So, if I further solve it, what will I have? 1.25 minus 2.5 cos omega t equals to RF by R1 minus RF by R2 into 0.5 cos omega t, right, 0.5 cos omega t. So, the DC input line contains resistance R1 and that can be calculated as nothing but RF by R1 equals to 1.25, correct, 1.25. This is very easy, right. Here you see this value RF by R1 or R1 equals to RF by 2.5. What is RF? RF is given 10 kilo ohm. So, R1 equals to 8 kilo ohm. Similarly, time varying signal input line contains R2, right. You can see here, you see the point here you have to understand is when you are considering DC input line, then you can see DC input line, right, it contains this value, but point varying signal, this contains this value, correct. Point varying signal, which is this one, it will have 2.5 cos omega t. So, I can write RF by R2 equal into 0.5 cos omega t is nothing but this particular equation, or R2 is nothing but this value, or further if I solve it, R2 would be 2 kilo ohms. Thus, I have found the value of R1, I have found the value of R2, and now I can put this value and design a summing amplifier, alright. So, it is very easy. Let us quickly once again see what you have done with summing amplifier. Summing amplifier is nothing but an inverting amplifier connected in a way that you have a lot of input voltages more than one input voltage. Here you can see, so that you can take a summation of those input voltages. It can be n numbers, okay, like this it can be until n, okay. This is R n, I n, V I n, right, n times, okay. So, point is that the formula is very easy. VO equals to feedback resistor RF, since it is inverting. So, minus RF by R1 we have seen, right. VO equals to minus RF by R1 into V1, this is the inverting amplifier, right. Now, here we have minus RF by R1 into V1 plus we have, or minus plus we can also write minus RF by R1 into V2 plus again we have minus RF by R3 is R2 into V3. So, if I solve this, I will have this equation, right. Once I know this equation, if I am given a problem, which is shown here, that for the output voltage, given output voltage, if you have two signals, input signals, and you have feedback resistors, then we can solve the value of R1 and R2, because there are only two voltages V1 and V2. So, we have to find R1 and R2. We are given the value of RF, we are given the value of VO, right. We are given the value of V1 and V2, everything is given. So, life becomes very easy, because we have to just substitute the value and solve it, and then we know that this is the DC input line, this is the resistance R1 that is the DC input line contains, and then we see the time varying signal, this is the time varying signal, and it is related with this particular signal. So, then we can find the value of R2. Thus, R1 and R2 is very easy to find, all right. So, let us see one more example of summing amplifier, okay. So, what will be output voltage of op amp? Inverting adder, it is also called inverting adder. For the input voltage is V1 is given, V2 is given, V3 is given, R1 is given, R2 is given, R3 is given, and feedback resistance considered to be 2 mega ohms, RF is also given. You see, life is so easy, this is so easy question, everything is given, V1, R1, V2, R2, V3, R3, RF, everything is given, right. Now, output voltage is what? Output voltage is VO equals to minus K. So, K is nothing but, this is nothing but gain factor, right, RF by R1, that is the K, okay. RF by R2, K2, RF by R3, K3. So, minus bracket K1 V1 plus K2 V2 plus K3 V3. So, if I substitute the values, then what will happen? K1 is nothing but RF by R1. So, if I substitute values 2 mega ohm by 600 kilo ohm, I will have 3.33 which is my RF by R1 or K1. Same way, if I substitute value for K2, that is RF by R2, 2 mega ohm divided by 300 kilo ohm, I will have 6.66, right. And then finally, for K3, RF by R3, 2 mega ohm by 2 mega ohm is 1. So, I have now 3 values. If I substitute those values in this equation, what will I have? VO equals to minus 38.3 volts. Hence, the final output voltage of an inverting amplifier is nothing but the summation of all the input voltages estimated to be in terms of negative voltage of about 38.3 volts, about minus 38.3 volts, negative voltage is minus the 38.3 volts, okay. Very easy. This is how the summing amplifier can be solved. So, what we have seen in this particular module is that we have seen that we can use the operation amplifier as an inverting amplifier, and then we have solved few problems. Then we have also seen the operation amplifier as a non-inverting as a summing amplifier, and we have seen a problem how it can be used as a adder or as a summer, right, or the summing amplifier. Now, in the next module, let us see how we can use operation amplifier as a non-inverting amplifier, okay. So, there are several applications, like we have seen the slide 1, that the op amp can be used as a inverting, non-inverting, differentiator, integrator, summer, right. So, we will see few other circuits in the next module. Till then, you just look at what I have taught in this particular module, and I will see you in the next module. Bye, take care.